Hello folks, in this video we're going to look at equilibria and how equilibrium is related to changes in the Gibbs energy. So we first look at a graph here where we have what's called the reaction coordinate along the horizontal axis. On the left side we have reactants, on the right side we have products. So as a reaction proceeds, we generally start with reactants and it proceeds from left to right in this graph to the formation of products. So over here on the left, that's just reactants and no products, and over here all the way to the right, it is products and no reactants. Anywhere in the middle, we have a mixture of reactants and products. Then on the vertical axis, we have the Gibbs energy. So how does the Gibbs energy proceed as we go along the reaction coordinate from reactants to products? Well, suppose we have something like this, so that we start out with the Gibbs energy of our reactants at this point right here, and the reaction proceeds toward the formation of products. You notice the Gibbs energy is dropping, reaches a minimum, and then the Gibbs energy increases to the point where we have just products and no reactants. Well, what does that mean? Well, the equilibrium between the reactants and products is going to be at the Gibbs energy minimum. Now remember, when we talked about the Gibbs energy, we talked about a constant temperature and pressure process. We know that delta G is less than 0 for a process that has delta S for the universe greater than 0. That is, the second law of thermodynamics will drive the Gibbs energy toward a minimum. All right? And so that's how these processes will occur, and again, constant temperature and pressure, of course. But the process always moves in a direction to decrease the Gibbs energy until it reaches a minimum. And then at the minimum, we have delta G equal to 0, and that means that we are at equilibrium. So the point of equilibrium is the Gibbs energy in this plot. Now I've drawn it in this case so that it's pretty close to the middle where we have equal amounts of reactants and products, and of course it need not be that way. We could have a minimum over here where we have mostly reactants and very few products, or over here where we have mostly products and no reactants. And of course, at this situation here, if the minimum occurs where we have just products, then the reaction goes to completion. All right, so that's the point of equilibrium. All right, so what determines the point of equilibrium? Well, this goes back to our discussion of the Boltzmann distribution. At equilibrium, we have a situation where if we look at the reactants and the products and put the energy levels together of the reactants and products, we have a Boltzmann distribution. Now, so we have this plot over here on the left, all right? And the reactants for a simple reaction of A going to B, we see A here, the energy levels corresponding to the reactant A, okay? And B, here the energy is corresponding to the product B, okay? Now this is an endothermic reaction because the products are at higher energy than the reactants. So we know for one we have an endothermic process in this particular case. So at the point of equilibrium we will have a Boltzmann distribution. So if we merge the energy levels here in blue of the products with the energy levels of the reactants and then use the Boltzmann equation to calculate the relative population of these energy levels, this is a distribution we would get. And in this particular circumstance, it's an endothermic reaction. The density of energy levels for our reactants would be fairly high, and you can see probably from this diagram that at equilibrium we're going to have more reactants than products. And so that means with our equilibrium constant, which we're going to talk about in a few moments, the equilibrium constant, which you have certainly seen before in other classes, is going to be less than 1 when we have a situation where the products are less than the reactants. And I hope this is kind of clear. And again, so we have an endothermic reaction here in this circumstance, and we've got more reactants in red than we have products in blue. Now over here on the right, we also have an endothermic reaction because the product energy is still higher than the reactant energy. But in this case, the reactant energy levels are very farly spaced apart. And that means that because they are spaced apart by such a great amount of energy, that we have a situation where we look at the Boltzmann distribution, we're going to find that we have here, and this what's shown here, we have these four energy levels are going to be populated according to the Boltzmann distribution, but we're going to have far more energy levels of the product populated, represented in blue. So that means that even though it's an endothermic process, this represents a situation where the product energy density is greater. So at equilibrium, we're going to have more products than reactants. So that's a simple statistical explanation for the point of equilibrium. Let's go ahead and look at things from the more classical thermodynamic perspective. All right, the first thing we're going to do is introduce something called chemical potential. We know that from our discussion in the last video, that we represent the Gibbs energy dependence versus pressure and temperature by this fundamental equation here. If we have a mixture where we have more than one component, then in addition to considering the dependence of the Gibbs energy on pressure and temperature, we must also consider the dependence of the Gibbs energy on the number of moles of the various substances present. So that means we need to add a term here which represents the dependence of the Gibbs energy on the number of moles of a particular substance I, and we need to include all of the substances that might be present in a mixture. So this is a more complicated expression, but basically we simply add a composition term for everything that's present, and we have a partial derivative for everything that's present. Now, this may seem confusing at this point, but hopefully as we go through this, young Padawan, we will find that this is more easily understood. Now, since this compositional term and this partial derivative representing the dependence of the Gibbs energy on the number of moles of a particular substance is very, very important in chemistry, because obviously when we're talking about chemical reactions, we're talking about having more than one component present. We at least have one reactant and one product. So we need to include this term when we're talking about chemical reactions and the changes in the number of moles of the various species present. To do that, to explain that, or to accommodate that, we introduce something called the chemical potential, represented by the Greek character mu, such that the chemical potential is very simply equal to this partial derivative, which represents the dependence of the Gibbs energy on the number of moles of a particular substance. Now, if we only have one substance present, in other words, we don't have a mixture but just one substance, the chemical potential actually reduces very simply to the molar Gibbs energy. It's just the Gibbs energy of 1 mole of substance. All right, so we all know that we always compare our thermodynamic quantities to values at standard conditions, and so that's what we're going to be doing here in our discussion of equilibria. We're going to be dealing with this relative to standard conditions. So again, just to reestablish standard conditions, when we talk about pressure, we're talking about 1 bar pressure, and of course we represent standard conditions by the little naught, P naught superscript. When we talk about concentration, standard conditions is 1 mole per kilogram or 1 mole. A lot of times, because we're dealing mostly with aqueous solutions, we will just approximate this with 1 mole per liter of solution. And the biochemical standard conditions corresponds to a pH of 7. All right, so now if we're dealing with substances in a reaction, we could have gases, and if we have an ideal gas, then the chemical potential of the gas relative to 1 bar pressure is given by this simple expression here. And this just goes back to the pressure dependence of the chemical potential that we learned about previously. So the chemical potential of a substance, which we're calling A, is equal to its chemical potential under standard conditions, 1 bar pressure, plus RT, R being the gas constant, of course, times the natural log of the ratio of the pressure of substance A to the standard pressure, which of course is 1 bar. If we're dealing with something in solution, if we're dealing with a solute, then this equation will simply change to RT-ln. We're dealing with molality here, so the little m represents molality. The molality of substance A divided by 1 mole per kilogram. But those correspond to ideal circumstances. With an ideal gas, of course, we're not talking about interactions. We ignore interactions in the case of an ideal gas. In the case of the solute, when we're talking about this, we're ignoring things like solute-solvent interactions in these in this particular approximation. Reality, of course, will often rear its ugly head, and so to deal with that, we substitute for pressure and molality something called activity. Now, we're just really talking about activity here. We are probably, most of our calculations, going to be using molality or pressure, but we need to understand that under non-ideal circumstances, which is frankly most of the time, we're going to we have this activities to compensate for interactions that are not addressed in these two equations. All right, so let's consider what happens when we have a reaction where we have reactants going to products. The lowercase letters here represent the stoichiometric coefficients. And if we want to determine delta G for the process of reactants and products, we can use the chemical potential. So in this particular circumstance, we've got, actually this needs to be rewritten, but we have a situation here where we have the products minus the reactants. Okay, so I've corrected the stoichiometric coefficients in our equation here. So what we have is delta G for a process is equal to T, the stoichiometric coefficient for D, times its chemical potential. And so what you see here is the products, their chemical potentials multiplied by their stoichiometric coefficients, minus the reactants with their chemical potentials multiplied by the stoichiometric coefficients. Again, so it's products minus reactants. All right, now if we go ahead and substitute the expression that we looked at on the previous slide, which relates the chemical potential to the standard values, so all we're doing is substituting, for example, for the chemical potential of D, the standard chemical potential plus RT times the natural log of the activity. Again, we've got products minus reactants. All right, and if we put all this together using the properties of logarithms, we have this expression here where the chemical potentials, products minus reactants under standard conditions, is just delta G naught. All right, and then with the logarithmic combination here, combining the terms, we have the activities of the products raised to their stoichiometric coefficients divided by the activities of the reactants raised to their stoichiometric coefficients. And of course, you may recognize that from your previous chemistry courses. That is what's called the reaction quotient. All right, so here is our reaction quotient that's in the previous slide. Products raised to their coefficients divided by reactants raised to their coefficients. So we can simplify our expression for delta G at a particular set of activities for products and reactants. Delta G is equal to delta G naught plus RT ln of Q. And of course, you remember from general chemistry that the reaction quotient, it looks like the equilibrium constant. So how does it relate to the equilibrium constant? Well, so at equilibrium, we're going to note that, as we saw in the first slide of this presentation, that delta G is equal to 0. That's the minimum in the G versus reaction coordinate curve. So delta G is equal to 0 at equilibrium, and so that means 0 is equal to this delta G naught RT ln of Q, with the proviso that we are talking about the equilibrium concentrations or activities of our products and reactants. All right, and so defining that particular reaction quotient with activities of products raised to coefficients divided by activities of reactants raised to coefficients. We define that as the equilibrium constant. Of course, you've seen this before. This is how we calculate equilibrium constants. We use products divided by reactants. And so under those circumstances, making that substitution here for our reaction quotient, we note that delta G naught is equal to negative RT ln of K. So that's one way we can determine the equilibrium constant for a particular reaction by determining delta G naught for that reaction. And of course we can do that by using tabulated values of the standard Gibbs energies of formation of our reactants and products. So we can use those tabulated values, we can calculate delta G naught, and then from delta G naught we can calculate the equilibrium constant K. All right. Now I do want to emphasize something here, and that is that the delta G naught represents the equilibrium constant, so we can calculate that. If we have a situation where the equilibrium constant is less than 1, we'll note that delta G naught will be positive. If we have a situation where the equilibrium constant is greater than 1, we will note that delta G naught is negative. So we will say, if we calculate delta G naught for a process, we will say that if delta G naught for a reaction is less than 0, that reaction is product favored because K is greater than 1. If delta G naught for a reaction is greater than 0, we say that reaction is reactant favored because the equilibrium constant is less than 1. So let me just reiterate. If delta G naught is less than 0, the equilibrium constant is greater than 1, and we refer to that as being product favored. If delta G naught is greater than 0, the equilibrium constant is less than 1, and we refer to that as being reactant favored. The tendency is, and this is frequently how it's taught in introductory chemistry courses, the tendency is to calculate delta G naught, the standard conditions for delta G, and if that is less than 0, the tendency is to say, well, the reaction is spontaneous. If it's greater than 0, the tendency is to say that the reaction doesn't occur. The reality is, though, when we're talking about delta G naught, we're not talking about the spontaneity of a reaction if all of the substances are not under standard conditions. The better way to discuss delta G naught and the impact of sign is to look at it this way. If delta G naught is less than 0, we know that we have a product favored reaction. If delta G naught is greater than 0, we know we have a reactant favored reaction. So this concludes our discussion and introduction to the equilibrium constant and the Gibbs energy. In the next video, we'll look at the dependence of the equilibrium constant on temperature and pressure and Le Chatelier's principle, and how that is impacted by delta G. Until then, have a good time.